In this video, I'd like to explore solving one-step equations, and in order to do that, we first need to look at a couple of definitions. The first thing we need to study is what an equation is, and we notice that an equation is a mathematical sentence. So we can fill this in: mathematical sentence that states two expressions are equal to each other. So think of it kind of like an English sentence, but instead of there being words that tell a story, we instead have numbers that we're relating and calling equal to each other. So down here, I have some examples. I have two different expressions, 3 plus 4 and 7, and I'm claiming that those are equal because of our equal sign in the middle. And same over here, two different expressions, 12 divided by 4 and 3, and this is a mathematical sentence, and we're claiming that these are equal to each other by our equal sign. Next, what we want to study is what a variable is. And we notice that a variable is a letter or symbol used to represent an unknown value. Unknown value. And here we see that the letter used is the letter X. So we're asking 3 plus some value has to equal 10. And 3 times some unknown value, X, has to equal 12. We're going to notice that one of our goals is to find what that variable is. And this is what solving is. So when I say what does it mean to solve an equation, we notice that to solve an equation means to find all values, and notice the S here. This S is implying that there could in fact be more than one solution. But we want to find any solutions that do exist that would create a true equation. So here I have this example, 6 minus x equals 4, and we say that the solution, I'll underline that, is x equals 2, because if I take that 2 and put it in for x, which is what I see over here, I notice that this produces a true statement, 6 minus 2 equals 4. So we're trying to look at the variable and think, well, what could I put in for that variable that would make this a true statement? So the question is, how do we solve it? Sometimes we can just look at the equation and know, but other times it might take a little bit more work. So we notice that we solve an equation by isolating the variable. Isolating the variable. And isolating sometimes can be misinterpreted, so we want to note that this means we need to get the variable alone or by itself on one side of the equation. And we're going to do this by applying the inverse operation. And we notice that inverse is another word for opposite. So I'm going to underline that word opposite. And we also need to apply this to both. I'm going to put this in capital letters because it's so important. Both sides of the equation. So I can't just apply it to one side. I have to apply it to both sides. And we'll see in action why that's so important. Okay, so before we jump into a problem, let's review what the inverse operations are. If I give you addition, hopefully we think of inverse, or the opposite of addition, as subtraction. And likewise, if we have subtraction, the inverse of subtraction is addition. And the inverse of multiplication, or the opposite of multiplication, would be division. And then the inverse of division then would be multiplication. So what we're going to do is apply these inverse operations to whatever operation is with our variable, see if we can get that variable by itself, and we're going to notice that this means we've solved the equation. So here's our first example I want to look at. We're asked to solve this equation, x plus 3 equals 5. So I have my two expressions, x plus 3 and 5, and the claim is that these are equal to each other, and what we need to do is figure out, well, what is x? So what I want to look at then is I want to look at, okay, well, what is connecting to the x? So we want to zero right in on the x, and I'm saying, looking right here at the x, what is connected? And the answer is this 3 here. I can see that the 3 is the only thing on the side of the equation with the x, And most importantly, I notice that the only thing with the 3 is addition, right? If I look right at that sign, we're adding the 3 to the x. So I have to think, well, what is the inverse of addition? And hopefully we're thinking right now subtraction. So I'm going to apply the inverse, minus 3, to both sides. And the sides of the equation is very important. I often like to put a line right down through the equal sign here. So now I'm going to apply the negative 3 to the side with the x. I'm going to apply the negative 3 to the side that does not have the x, both sides of the equation. So this leaves me with this new equation, x plus 3 minus 3 equals 5 minus 3. And what we're noticing on this left-hand side, or at least the goal is that on this left-hand side, these inverse operations, addition and subtraction, are going to kind of eliminate each other. Or in this case, we're noticing that that negative 3 and the positive 3 are going to add to 0. So I'm going to have x plus 0 equals, and then 5 minus 3 will just be 2. Lucky for us, I don't really need to write x plus 0, so our solution is just x equals 2. Now every time we find a solution, what I want to do is check this by actually taking our solution, which in this case is 2, and I want to put that 2 back in for x. Okay, so I'm going to check this. We're going to start with our original equation, x plus 3 equals 5. And I'm going to replace this x with the solution we found, 2. So I'm going to replace that x, right where the x used to be, with 2. And I'm going to ask, well, is this a true statement? And I can see here that 2 plus 3, if I combine those, I do get 5, which means that we have done this equation correctly. But it's always good to check our solutions. In this problem, again, we want to focus on solving for x, and we're going to immediately look at the left side of the equation and ask, well, what is happening to x? What is the operation that we have to apply the inverse of? And I immediately notice that we have this subtraction of 4/5, which means I need to apply the inverse of subtraction, which is addition. So here we go. I'm going to go ahead and split my equation into two different sides. I'll draw this line right down the middle. And now what I want to do is apply the inverse. So I'm going to add 4 over 5, again, addition being the inverse of subtraction, to both sides. So this will give us the new equation of x minus 4/5 plus 4/5 is equal to negative 2/3 plus 4/5. Okay, now the left-hand side is actually pretty easy. Because of our nice application of inverses, I notice that negative 4/5 and positive 4/5 simply add to 0. So we're left with x plus 0 here. The trickier part is over here on the right. In order to add these two fractions, I notice that I have two different denominators. I need a common denominator. So I'm going to come over here and I'm going to say, well, I need negative 2/3 and 4/5 to both become a number with a common denominator. 3 and 5 both go into 15. So I'm going to make these both into a denominator 15. I can multiply 2/3 by 5 over 5, 4/5 by 3 over 3, and I can change this into negative 10 over 15 and 12 over 15. And now with our common denominator, I can add these together, and I find that our solution is x equals negative 10 plus 12 is 2 over 15. Good, now with a complicated solution like this, definitely worth coming over here and checking our answer. So I'm going to plug in. I'm going to start with my original equation, x minus 4/5 equals negative 2/3. So here we go, x minus 4/5 equals a negative 2/3. And I'm going to plug in that 2 over 15 for x. So I'm going to say 2 over 15 minus 4/5 equals a negative 2/3. And I think it's going to be a little bit easier to check if I once again make all my denominators the same. So I will again want to make the 5 and the 3 both into 15. So I'm going to multiply the 4/5 by 3 over 3, the 2/3 by 5 over 5, and that's going to give me this new equation, 2 over 15 minus 12 over 15 equals negative 10 over 15. So now I just need to confirm that this is true, and if I look at 2 minus 12 on the top, I do get negative 10 over 15, which equals my second fraction, negative 10 over 15. On to a third example. This time we notice that I have a different operation connected to x. I again want to get x by itself to solve, but this time we have 4 times x. Remember, if there's nothing written beside it, I assume that it's multiplication, and the inverse of multiplication is division, so I'm actually going to apply division to both sides. But again, I'm going to go ahead and drop that line down the middle. I'm going to apply the inverse of multiplication by 4, which is division by 4. Division by 4. And we can write this new equation as 4 over 4x equals 28 over 4. And the thing that we want to recognize here, why multiplication and division are inverses, is that this new fraction we have, 4 over 4, is just 1. And I can write 1x if I want, but multiplying by 1x really doesn't do anything. So I actually have solved here just for x. So again, I'll say that again. 4 divided by 4 is 1. I don't need to multiply by 1, so we really are just down to x there. And on the right-hand side, I see that that 28 over 4 divides to 7, which is why we now have the solution x equals 7. And I'll write that again down here. And again, a good way to make sure we did this right was to check. So I'm going to write 4x equals 28, which is my original equation. In place of the x, I'm going to put that 7. And again, we do recognize that if there's nothing there, it really is multiplication. And I can see that 4 times 7 is 28. So we have done this correctly. A fourth example here. I'm again going to try to solve this equation for x. So I'm looking at this side of the equation that contains x. And I notice that 4 is in a fractional form with x, which means 4 is dividing x. And now, because I recognize that division, I have to think inverse. And the inverse of division is multiplication. So I'm going to multiply both sides. So I'm going to take x over 4, and I'm going to multiply it by 4. And if I do it to the left-hand side, then that means I have to take the 3 and also multiply that by 4. Okay, and this is actually going to result in a very similar case. On this left-hand side, I don't have it written explicitly, but we can always assume that anything that does not have a fractional denominator is being divided by 1. So really what we have here is 4 over 1 times x over 4. And this is going to give us, if I multiply straight across, 4x over 4, or in other words, 4 over 4 times x over 1, which would be equal to 12. But again, if I look at this fraction 4 over 4, here's our inverse work going. 4 over 4 is just 1 again. I really don't need this. So a lot of times we use that word cancel, and we just say that when I multiply and divide by the same number, this really just cancels because we're now just multiplying by 1 and we don't need to write that. Which means that x is now just going to equal to 12. So let's go through that one more time because that's a little tricky. We recognized up here in our original problem that we're dividing by 4. The inverse of division is multiplication, so then right here we multiplied by 4. right here, or the 4 over 1. We multiply not just the left-hand side, but the right-hand side as well by 4. We recognize that when I multiply both sides by 4, this left-hand side, I'm multiplying and dividing by 4, which really gives me the fraction 4 over 4, which is just 1. And since I don't need that 1, we're left with just x is equal to 12. And if we're still not convinced, we can always come over here and check. I have x over 4 equals 3. I want to check this by plugging in 12 for where the x used to be. And we can double check that 12 over 4 in fact does simplify down to 3. So we've done this correctly. Last example I'd like to do together. This is a little tricky. I have this fraction here of 2/3. And we notice that 2/3 is really being multiplied by the x because, again, there's nothing in between. If I get rid of this box and I look right in between 2/3 and x, I notice there's no operation, so we're assuming multiplication. Now, we can think of this then as, well, if I want to cancel that multiplication, we use addition because that's the inverse. But here's the problem. If I write this out, that means I have 2/3 x divided by 2/3 equals 5 divided by 2/3. Now this is really messy, right? Dealing with all these fractions. What I want to do is think back to what we did earlier when we divided by fractions. If we remember, dividing by a fraction is really the same as multiplying by the reciprocal of the denominator. So what I'm saying is, instead of dividing both sides by these 2/3 here in the denominator, how about we just multiply both sides by the reciprocal, or in other words, that flipped fraction. So that flipped fraction would be 3 over 2 times 2/3 x. And I'm going to do that on both sides. So that's going to equal 5 times 3 over 2. And again, I can imagine that that 5 is over 1 since I don't have any denominator there. And again, just to be clear, all I did there was flip these 2/3 in the bottom, and that gave me these 3 over 2's here. Right? There came that first 3 over 2 there, and there's my second 3 over 2 here. So now I'm able to multiply, and I'm just going to go right across. So 3 times 2 and 2 times 3, that gives me 6 over 6x. And we're in good shape here because we actually notice that, again, 6 over 6 is just 1. And I really don't need this 6 over 6 because I don't need to multiply by 1. On the right-hand side, this is going to be equal to 15 over 2. And there's our solution. I'll bring that up here on the top on the right-hand side. X equals 15 over 2. Right, I've solved because I have nothing left on the left-hand side besides this little x term down here. So let's check this. If I plug in to 2/3 times x equals 5, I'm going to put in for x that 15 over 2 we just found. So here we go, 15 over 2 equals 5. I multiply across, that gives me 30 over 6 equals 5, which I notice does simplify down to 5 equals 5. So we've done this correctly. At this point, you'll notice that there are 4 problems at the remainder of your packet that I've asked you to do on your own. I'd like you to give those 4 problems a try by solving and then checking your solutions, and we'll start next class by looking at these problems.